Hey guys, I just wanted to walk you through the solutions to your topic 10.2 handout, and I'm actually re-recording this video, so fun times, fun times. So, first question, you were asked to evaluate the speed of a satellite in orbit at a height of 500 kilometers above the Earth's surface, and a satellite that just grazes the surface of Earth. And we should assume that the radius of the Earth is 6.38 times 10 to the 6 meters. Okay, all good so far. Note that they don't give us the mass of the Earth, which we actually we need according to your data booklet, which is right here. So the data booklet says that orbital velocity is equal to the square root of the gravitational constant times the mass of the object being orbited divided by the orbital radius. Okay, so at the surface of the planet, we can plug in our numbers and everything is pretty easy, pretty straightforward, just algebra, and you will find that your final answer is 7.9 times 10 to the 3 meters per second, or 7,900 kilometers per second. You'll note that this magnitude of velocity comes up a lot when we're dealing with orbits around planet Earth, and it's a good way to very quickly check your answer. Is your answer around 7,000 or 8,000 meters per second? If the answer is yes, your calculation is probably correct. If the answer is no, you might want to double check things. Okay, so there is our first bit. Next, we have a satellite that is just grazing the surface of the Earth, okay? Or actually, that was our first calculation. So our second calculation is the velocity of the satellite in orbit. And we're going to find that the orbital velocity is a little bit slower. Note also that here, our radius is going to be the sum of the radius of the Earth plus the distance from the Earth, okay? And that shouldn't be really surprising. Also note that they give 500 kilometers, and you will need to convert that to meters, which is a step that students often forget. And trust me, the IB will predict that, particularly on paper 1 style questions, and give you the wrong answer because they are mean to you. Okay, again, note that our answers around 7,000 or 8,000 kilometers per second. So as expected. If it's not something like one of these two values, you need to double check your work, very likely. Okay, 10.10, a satellite is in low orbit, experiencing a small frictional force. Also note that for this question, particularly on the surface, we're definitely ignoring air resistance because that's going to very rapidly change our velocity, especially at this velocity. So we're assuming that Earth is a lifeless shell with no atmosphere. Okay, so a satellite in low orbit experiences small frictional force due to the atmosphere in a direction opposite to the satellite's velocity. Explain why the satellite will move into an orbit closer to the surface. Okay, for part A, we know that friction from air resistance is going to decrease the kinetic energy of the satellite. Okay, so when that happens, our total energy is equal to negative kinetic energy. And here's the weird part. This is kind of unintuitive. So if we decrease the kinetic energy, then we're making this value more negative. So what that means is we're increasing the magnitude of total energy, which is bizarre. So if we increase the magnitude of total energy, then velocity is going to increase as well, as we know that velocity squared is proportionate to kinetic energy. And we know that from our formula for kinetic energy. E is equal to 1/2 mass times velocity squared. Yay. Okay, 10.11. A probe of mass m is launched from the surface of a planet of mass m and radius r with kinetic energy given by this equation. So we have small m and we have large m, and this is a pretty logical way to denote a smaller mass and a larger mass. So, first bit. Explain why this probe will not escape the gravitational field of the planet. Well, first thing we need to do is a little bit of math. So we know that kinetic energy in the system is equal to 4/5 times the gravitational constant times the large mass divided by the large radius. We also know that kinetic energy is equal to 1/2 mass times velocity squared. Okay, so we can solve this equation then for velocity, and what we find is that velocity is equal to 8/5 times the gravitational constant times the large mass divided by the small mass times the large radius. Okay, or the radius of the orbiting object in this case. We also know that escape velocity is equal to the square root of 2 times the gravitational constant times the mass of the object and the radius of the object. Okay, so if these two velocities, these two equations are true, then we can not exactly equate them, but what we can say is that our velocity should not be greater than our escape velocity. Okay, if our velocity is greater than our escape velocity, then we've got a problem. So that is what this statement is saying. Here's our actual velocity, which we could call v sub a or whatever, and here's our escape velocity. Okay, so there we go. All right, so what we find then is that 8/5 divided by the mass of the probe should not be greater than 2. So in order for the probe to escape, 8/5 divided by the mass of the small object, it must be greater than 2. And if that is the case, then our probe will go bye-bye. But our probe is probably going to have a mass of hundreds of kilograms, okay? And remember that as this small m gets larger, 8/5 becomes smaller and smaller and smaller, okay? And it's already less than 2. So it is impossible that any object with a mass above 1 kilogram would achieve escape velocity. You will find that your book takes a different approach, and you should take a look at it. Okay, B, the probe eventually settles into a circular orbit around the planet. Calculate the radius of its orbit in terms of r. Okay, so first thing we do is we set up our equation where total energy is equal to kinetic energy minus potential energy, and we plug in the values that we have been given, where we have 4/5 times the gravitational constant times the mass of a large body times the mass of the small body divided by the radius, okay? And we subtract from that our potential energy at that radius, and I don't particularly want to read those variables again. But what we then find is that our total energy is equal to negative 1/5 times gravitational constant times the masses of the two objects multiplied together divided by the distance from the object. Okay, we also know that total energy is equal to negative 1/2. You can see it. No need to reread it. Okay, so if the first is true and the second is true, then we can equate them together. And what we will find after just a bit of algebra is that these values conveniently cancel out. And what we're then left with is the center to center distance r is equal to 5 divided by 2 times r, which is just the variable that they gave us earlier. Okay. Next example question, 10.12. Okay, so figure 10.29 shows the variation of the gravitational potential due to a planet and its moon with distance r from the center of the planet. So the center of center distance is given by d, and the planet's center is at r equals 0. The center of the moon then is at r equals d. Okay, so how to approach this? Well, the first thing we do is we look at the initial gravitational field. Okay, and what we will find is that the initial gravitational field is given by negative 3.9 joules per kilogram. And how do we know that? We know that because the radius of the planet is equal to 0.04 r. And actually, we know that that is the case because what we have here is an asymptote. Okay, so then we start from this point, negative 3.9. You wouldn't be blamed if you said negative 4.0. That would be fine. We start with negative 3.9 or negative 4.0, and then we go over to the other side, and we need to identify this point. Okay, from this point, the moon's gravitational field will capture the object, but up until this point, and basically you know that this is the point because it's the maximum, or minimum rather. From this point, the object will be captured. So what we need to calculate is the amount of work done from this point here to this point here. Okay. So what we're looking at then is a change in the gravitational field. And if there's a change in the gravitational field, we can calculate work. Okay, so setting up the problem, slightly tricky, but from here, very straightforward. And this should be negative 4 points. Wait a sec. No, that's right. That's fine. Okay. So negative 0.4 times 10 to the 8 joules per kilogram. That is our gravitational field. So here we can see our change in gravitational field. Here we have our mass, 850 kilograms. Again, we pulled these values from our graph. If you had negative 4.0 times 10 to the 8th joules per kilogram here, that would not be irrational or problematic in any way. So in any case though, once you do the math in your calculator or in your head, what you will find is that you have 3.0 times 10 to the 11 joules for your work. Okay, next problem, 10.13. The escape velocity from the surface of a planet of mass m and radius r is given by, ta-da, and that is in your data booklet. So a probe is launched from the surface of the planet with a speed that is half the escape speed. Calculate in terms of r the largest distance from the surface of the planet the probe will get to before falling back down to the surface. Okay, so here's a little diagram that I drew just to show the parabolic path that we would expect our probe to take, and its maximum height then will give the distance from the planet. Okay, at the probe's maximum distance, our total energy is going to equal kinetic energy plus potential energy, and at the apex of that parabola, our kinetic energy should be 0. I've shown a little bit of horizontal motion here, but we're assuming that it has been launched perfectly vertically. Okay, and that will give us 0 kinetic energy at its apex. So total energy in this case is going to be equal then to the potential energy, as you can see here. Okay, so at launch, our total energy is going to be given by kinetic energy minus the gravitational potential energy. And at the planet's surface, that value is going to be 0, but here we're just doing a little bit of algebra, so hold off on throwing that away. The bit of algebra we need to do is to plug our escape velocity in. So our kinetic energy then will be 1/2 mass times the escape velocity halved, and that value will be squared. Remember, we're told that the probe is launched with a speed that is half the escape speed, so that's what we're plugging in here. Okay, a little bit of algebra that I've skipped will produce the next equation. As you see here, 2 squared is 4, 4 times 2 is 8, that's where we get our 1/8. And as you can see, this is why we have not gotten rid of this, even though its value should be 0, because it's still algebraically useful for us right now. Okay, so using the magic of algebra, no, actually at the surface of the planet that would be non-zero. I take all that back. Okay, sorry, my bad. Anyway, so we finish off our algebra, and what we find is that we have negative 3/4 times the gravitational, the universal gravitational constant times the large mass times the small mass divided by r, the distance from the object. Okay, so finally, we need to summarize all of this. So our total energy is going to be equal to negative gravitational constant times the large mass times the small mass divided by small r. Remember, we defined that in our first step. We also then know that we can express total energy in terms of large r, and it is given by the equation we looked at previously. Our negative signs cancel out, and we can, these cancel out, and we can then solve our equation. R is equal to positive 4/3 large r. So, bit of algebra. Last question, 10.14, the inevitable example. What must the radius of a star of mass m be that such that the escape velocity from the star is equal to the speed of light c? Okay, well, they tell us our escape velocity. We know that it's 3.0 times 10 to the 8 meters per second. Everyone should know that immediately off the top of your head. Okay, we then just do a bit of algebra, and we rearrange it like so. I don't really feel the need to walk you through it. It's fairly straightforward. So our radius then is going to be equal to 2 times the gravitational constant times the large mass divided by escape velocity. And this is obviously going to produce very, very, very tiny value. If you want to calculate it, go for it. Although we don't know the large mass of the object, so you would have to find one. You could use the mass of our star as an example if you wanted to. Anyway, this value is called the Schwarzschild radius, and any mass compressed to this value would be a black hole, what we call a singularity. Okay, well, guys and ladies, it's been super fun. I hope you enjoyed the video. Do not click like, do not subscribe.